Now let's try an example where we translate an English sentence into symbolic form and then build a truth table off of that, okay? So the first thing I have here is a statement, if x makes a denominator 0 or a radicand negative, then x is not in the domain. Now this is actually a theorem in algebra, it could be seen as a theorem. And basically, if you're looking at a function or something that you plug numbers into to get numbers back out, anytime you end up with a denominator of 0, you have an undefined expression or function. So if you had a function like 2 over x plus 3, well, if you plugged in a negative 3 here, you get 0 on the bottom and the function is undefined. But everything else would work. If you're radicand, now a radicand is the numbers under a radical. So if you had a radical is like a root, so if you had like the square root of x plus, 8, then, if you put in for x, if you put a negative 10 in for x, negative 10 plus 8 is negative 2, and you can't do the square root of a negative 2, without getting into complex numbers and stuff. So anyway, that's kind of the background behind this. The domain is all the x values that you can put in and get something valid out, get a real number out. So we say if x makes a denominator 0 or a radicand negative, then x is not in the domain. Now how do I translate that and look at truth tables? Well, first of all, I have to break it down and put it into symbolic form. So let's call one of the statements x makes a denominator 0. So just kind of separate this off around the connectives, right? The if then is a connective, the or is a connective, the not, connective, and the not is a connective, right? So those are the things, if then, the or, and the not. So we've got to break it up around there. So x makes a denominator 0. Let's call that the first statement. Let's take q to be x makes a radicand negative. So obviously the way it's worded in English, we don't include that little part of the phrase, but that's okay. It kind of distributes to the other side there. So x makes a radicand negative. Most people have never heard the word radicand before, right? So the radicand is what's under the radical. And then of course, let's ignore the not. Let's say x is in the domain. That will be my third statement. X is in the domain. All right, so these are my three simple statements. Now we're going to try to work with them and put this into a symbolic sentence, a compound statement. So first of all, I have the if then. And I'm going to say the if then seems to be the most dominant part of this statement because the or, the disjunction, is contained within the antecedent, and the not is contained within the consequent. So you really have two big parts here, the if then, and then within that you have the or and the not. So let's write this out as if the disjunction, then the negation. All right, so now I've got the structure in terms of my the connectives. So then let's put the P, Q, and R in there. So P or Q, and then if P or Q, then not R, right? X is not in the domain, so that's not R. Okay, so that's symbolically what we're looking at. So now I've got to make a truth table with PQR, and then I include not R, and then kind of build this up. So this is going to be a little bit bigger because I have three simple statements. And so I really need a lot of rows here. So remember, with three simple statements, I need 8 rows, right? That's 2 to the third. So this will be 4 of them will be true for P. 1, 2, 3, 4, and 4 will be false. 1, 2, 3, 4, and then for Q, it's going to be half that. So 2 trues, 2 false, 2 trues, 2 false, and then for R, it's 1 of each going down, right? So it's true, false, true, false, true, false, true, false. And that should give me all 8 of my combinations. Then, so that's for PQR. Now I need not R. Actually, let's do this in order. You know, I kind of like, with an if-then statement, I kind of like keeping the antecedent first and the consequent second. It just, in my mind, that I'm not thinking about things backward in the table. So actually, let's go ahead and do that and go with P or Q. You don't have to do it this way. I just think it's going to be a little bit more clear. So P or Q, remember, disjunction is false when both are false. Everything else will be true. So just looking at P and Q, where's it false, false? To the bottom 2, right? So the bottom 2 rows are going to be false, false, and everything else will be true. So as long as one of those 2 is true, the whole thing will be true. Then I have not R, so the negation of R. And of course, that's just going to be the opposite of this entire third column. So it's going to be false, true, false, true, false, true, false, true. Instead of true, false all the way down, it's false, true, alternating. All right, so then with the conditional, if the disjunction, then the negation. And so remember, with a conditional, you want the antecedent to be true, the consequent to be false, in order to get a false, and everything else will be true. So I need true, false, which I have in the first row. True, 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 false. So third row. True, 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 false. In the 5th row. True, true, false, 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 true. That's it. So those are the only 3 places where you get true, false. Everything else will be true. So 2nd, 4th, 6th, 7th, 8th rows are all true, right? So that will be the truth table then for this statement. Now, if I had a number x, let's say I had a function, kind of an interesting mathematical example, a function like 2 over x plus 3 plus the square root of x plus 8, if that was my function, and I pick an x value of -3, well, according to the statement, x makes the denominator 0, so p is true. Right, so p is true, but x does not make the radicand negative, right? Oh wait, yeah, -3 plus 5 is, or -3 plus 8 is 5. So q is false. Then x is not in the domain. And so p is true, q is false. Let's see what happens in those 2 situations. So p is true, Q is false. So I've got a number that fits here and here, right? And so my statement is true only when R is false, which means X is in the domain. So if it's false that X is in the domain, which is correct, R is false, right? So I have to say that in order to make this true, P is in T, Q is in F, and P is true, Q is false, and R is false. And that will make the statement true, which in this case it is, okay? And then I could run the same sort of thing through for any other X value. Maybe I pick -8, in which case P is false, Q is true, R would be false. And then let's see, if I picked maybe something like X equals, I don't know, 0. Let's go with 1. X equals 1, that works. It's kind of a nice one. If I did X equals 1, well, X makes the denominator 0. Does 1 make it 0? No. So P is false. Does X make a radicand negative? Well, put 1 in there, I get 9. So no. So Q is false. And R, well, in order to make this statement true, R would, let's see, if both are false, right? False, false, and false, false, P and Q, then how do I make the statement true? Well, it's interesting. The statement is true regardless of the truth value of R. X is in the domain. Oh, fascinating. So you could have X in the domain or not in the domain. Oh, I see. Okay, so what's interesting here is this would tell you that that X could be in the domain, so 1 could be in the domain, or maybe there's another reason that it's not in the domain, I suppose. It's kind of interesting. Yeah, so this statement doesn't actually make any claims about what happens if X does neither, right? So if X does neither of these, if it doesn't make the denominator 0, if it doesn't make the radicand negative, we don't know anything about it. So in this case, the number 1 could be either true or false. Now, in our example, it's true that 1 is actually in the domain of this, but I could write a different function and find that 1 is not in the domain, even though it satisfies even though it makes P and Q both false. Let me show you that example. That's kind of interesting. Let's say I did a second function so that it's 2 over x plus 3 plus root of x plus 8 minus the log of x minus 1. Interesting. What I didn't state up here is that logarithms have problems. If the inside of the logarithm is 0, the x value is also not in the domain, but that's not part of my sentence. And so there's other reason here for R to be false. It's interesting. Yeah, I didn't see that one coming. So in this example, again, you can take the same value of x, P is false, Q is false, but in our case here, R is actually false, because there's another reason that it violates the definition. And this statement is still true. The original is still true. Actually here I can't say T or F, because R is actually in the domain of that function. So here's an example, I guess, where you have the same number picked. You got the F and the F, you got the F and the F, but here you've got a true, and this one you've got a false. So it can be the case in these two cases that you may end up with a true or a false consequent on the well, I guess that's not the consequent, right? Not R is the consequent. Well, I guess either way, then you have a true or a false on that column. Yeah, right there. So kind of an interesting example mathematically, but logically it also works out. So that's pretty cool. But what is interesting is that if you satisfy, like on x equals -3, if you satisfy one of them, the true, then you can guarantee as soon as you get the, if you satisfy one and not the other, then you can guarantee that R is false based upon the truth of the statement. If the statement were false, then you would have the opposite true. So cool. Making a little bit of sense anyway.